Hello, how are you? Good morning, good afternoon, good evening, depending on your location. Welcome to this webinar for that will be about the advanced structural concrete modeling using the new CivilFEM 2016. Okay, I am Ronald Siat, and along with me is Roman Martin, working in CIVIL, and we are pleased to present you these new capabilities for concrete. Okay.
Hi, good morning, good afternoon. About the new feature of new features of CivilFEM about concrete, advanced structural concrete, and the history about the modeling advanced concrete. The search of mathematical models is nowadays a great challenge. Because reinforced concrete is very complex, the behavior of reinforced concrete, and the mathematical problems is very high. But these barriers are being broken by CivilFEM, modeling these nonlinearities easier, faster, and improving accuracy. This webinar includes reinforcement concrete modeling in linear and nonlinear analysis to compare results, and we will see the unique advanced CivilFEM features for modeling nonlinear concrete behaviors such as concrete cracking for tension, nonlinear steel reinforcement as well, post-tensile cracking behavior, compression crushing, and also strain softening. To analyze all these capabilities, we will see three examples: multi-story building. We will solve with wind and cell elements the whole building, and also we will perform advanced nonlinear analysis on special points of these buildings, such as the shear walls or column beam joints. We will see a second examples, just seeing in detail the post-tension anchor zone in a girder bridge. And finally, we will see the creep analysis with a micropile. Well, let's start with the multi-story building. This multi-story building is made of beams and columns. So we are going to go to the software to run it. Here is the graphic interface. First here you have some options to save, open, or import frame models and the environment. Very important, select the codes we are going to use to check or design the model. I'm going to use Eurocode, but you can also select any code from a long list of the most important codes all over the world. Next step is creating the model. You can create points, lines, performing Boolean operations, but for creating the model, I feel much more comfortable using the script. Python is the language of CivilFEM, and here with this script, I've created here, you can see here, I've created here some parameters with the dimension size of the model, and here some loops to create different points, different lines in X, Y, and Z direction, and different areas here. So if I launch these commands here in my I'm going to display the script editor. Here paste the commands. We can also open from here a test file and run it. If I press play, save it, so it is creating. Here you can see in the output window all the points that are being created. Then we will create with the next loop lines, here you have, and with the next loop we will create areas. So it's very easy with these loops or using the graphic interface to create the model.
Yes, as you can use parameters, anytime you can change all of them, and so you can run every time with a different parameter with a different length of spans, with a different length of height of each column. So anything can be modified easily.
Well, the next step after the geometry is selecting the materials and cross sections. Here I'm going to select a material. Material classification is depends on the codes. I can select a concrete from the ACI code. In example, this one. Clicking OK. Well, I have this material. The default behavior is linear elastic, but I can modify it clicking here. And then instead of linear behavior, short-term load diagram. Press OK. And well, now we are going to use the parabolic law, and we have different ways to solve it with the parabolic law. The Puyo-Kusur plasticity, that is a model, special model for concrete behavior. Also multilinear elastic, if we are solving with elastic way but parabolic, or multilinear isotropic hardening. I'm going to use for the nonlinear analysis this one. And we can also add cracking behavior. Here the cracking behavior, clicking here we add the cracking properties we will see later in the nonlinear analysis. In my case, I'm going to leave here linear analysis, and the next step is creating sections, cross sections by dimensions, and adding reinforcement and so on. Well, and creating the mesh. I'm going to open the model, not to waste a lot of time creating the model. And well, this is my model. It's being open. And well, here entities we have these materials, concrete and steel. These cross sections, I'm going to plot one of them, reinforcement bars, and different structural elements for cells, beams, and columns. Okay. Well, here we have defined also, after defining the model mesh, we define loads, different loads groups. What we've done is creating the following load cases: live loads, spectral, and dead load. Here we added the spectra and well, different loads. We can plot them here, the load on the mesh, so we can see here the arrows of the different forces we have and pressures. We can plot the other one, load, that is here in the different stores, and well, the different data. Then after defining them, we press here solve it. It's very important the name of the load cases, because the name of the load cases will be the result file names. So after solving, clicking here, we solve in elastic model way. We can open those results, and in example we have the spectral results. As we added here in the loads, code 8 spectra, the software is performing the modal analysis. Here we have the data of the spectrum we are using. Is performing the modal analysis with the combination I select here, also the static load cases here, and after solving them I can find those results here. In example, the first mode, you open it and plot results. In example, well, displacement here, and well, here you have a mode shape. You can advance from one mode to the other here, pressing this button. Different displacements. Okay, well, after solving this, we have the different load groups, and we have to combine it. The way to combine it is pressing here, selecting result files, get load, if load have and spectral. I'm pressing OK. Then pressing OK. Here I will have the selected loads. Then I here define the name of the combination, ultimate limit state 1. Press OK here, and well, I add these load cases. Here I apply the coefficients and define all the combinations. After defining the combinations, click here and the software make the combinations, saving their subfiles with that name. After doing that, here I open the results and I have the combinations. In this case I created two combinations, ultimate limit state 1, ultimate limit state 2, and also serviceability limit state that is here, with different coefficients. Well, the next step is reading one of them. I'm going to read the ultimate limit state 1 and design by code. The way to design by code is using these bottoms here. I can check beams, axial, shear and torsion, and cracking. I've read the ultimate limit state, so I should take axial and bending. Clicking here axial. Well, here I have the information, the active code I have, the plane I'm checking. If I'm checking 2D, this is plane XY and XZ, or 3D. I check it, I'm not doing it right now, not to waste time, and well, after doing it, I create the results. Also for cells, I can design cells instead of checking, design cells, so the results are reinforcement amounts, and we can plot those results. Here, if I go to the slides.
In this case, we have selected the ACI 308 code, American code, but you can do it with any available code in CivilFEM.
So well, the procedure for this analysis is solving static response, static and response spectrum analysis, combine them. So if we are performing combinations, this is linear analysis, and then in post-processing level, we are designing by code. So we are solving with elastic linear behavior, but we are adding non-linear behavior in the post-processing, creating the integration diagram, taking into account this parabola rectangular law, and checking if forces and moments are inside, if we are checking or design calculating the minimum reinforcement amount for section to be okay. And well, some results we can see here. In example, I'm going to plot from columns. I'm going to select here from the structural elements and hide them all, but also I clear the loads, and I'm going to plot only columns. Columns start in the structural element with C. So well, these are the columns. Plot them, and well, I'm going to check if they are okay or not okay. So here in the results, after performing the bending plus axial checking, this one, I can plot the total criterion. If I go closer, or well, I also can plot with these lines. We can plot in lines and with this type of plot for the criterion, or we can also plot here in the real shape with the colors. You have both options. And we can see these sections are not okay in the joint places where columns and beams join together. So we know we have to increase reinforcement there and study in detail those points. Well, the same for cells. If I, well, cells clear.
The total criterion will be related to a kind of a safety factor. Okay, if the value is below 1, it will be considered okay, and if it's above 1, will be considered that second not okay.
Well, now we are going to see results or designing designing the cells, frames here, and well, we can plot reinforcement amount, X direction, plot.
We can use any units to plot them.
Well, here the units are square meters per meter. I don't like the units, that is square centimeters per meter, the one I would like to use. And well, I can see mainly I need more reinforcement in the shear walls, more than here in X top bottom. I'm going X top, let's see X bottom. Well, now also shear walls mainly, and well, also for Y direction, bottom. Here we can see also in the slabs we need reinforcement. Well, this is the reinforcement we need. Well, mainly what we've seen is that the most important points are the shear walls and the column beam connections. So we can study in details those parts with nonlinear analysis. Well, before going to that part, as Ronald said, the total criterion that we are plotting is the ratio between the distance from the center of the interaction diagram to the action we have, these points, the distance D1, and the ultimate capacity of the section. So the ratio between D1 and D2 is the safety factor we give. So if that is less than 1, section is okay because the action is inside the interaction diagram. If the point is outside, this is greater than 1, section is not okay. Well, after checking that, we can go further. Why should we stay there and perform a much more detailed advanced concrete modeling with the reinforcement details we got from the linear analysis that we did by code. Here we can combine some behaviors like cracking and crushing. So for tension and compression, we will have this behavior. So we will have parabolic low for compression, which follow nonlinear compression, isotropic hardening, or Puyu-Kusud. Also could be elastic, follow this line, or if that is nonlinear, if isotropic hardening will follow straight lines. And if we have selected crushing, when we reach a maximum strain, it will break the element due to crushing, with failure to crush it. And in the same way, in tension, we can define cracking stress and also a softening modulus. And for shear, we can combine with Drucker-Praget shear failure. With all these details, we are going to check shear walls with different reinforcement configurations and different holes possibilities. Let's see the software. We are going to open here, I don't save it, the shear walls. The first shear wall is this one. Here, if I select all the structural elements, here I have, well, we are seeing with the shape, but if I plot without the real shape, this is 2 beams and a cell element. Plot the thickness, and well, these beams are for giving stiffness due to the different floors, and this is the shear wall. What we are doing is applying horizontal force here. Here are the boundary conditions, and we will see the behavior of this shear wall. Reinforcement, we've defined it. We can see here are these, just in both directions. So I'll plot it all of them. After solving, I am going to check the results here. In example, I'm going to plot cracking. Y component of cracking. Well, I can see if I plot average results, I can see here I have, due to this horizontal force, if I plot with the deformed shape, well, the scale is very big. I can reduce it a little bit. Well, we can see due to this horizontal force, we are having here a big cracking zone due to in plane shear. So, well, I know this configuration is not very good. I'm going to check other configuration. The next configuration is this one, adding these diagonals and also bigger reinforcement here with higher diameter. If I check results, also I plot here all the elements. If I check results, also I'm going to check, so here, crack. Well, we can see we've improved the cracking behavior here with average. Due to those the reinforcement, we've improved the cracking behavior, just reducing in the mid zone.
Yeah, the strain was reduced.
Also, the crack strain is much smaller. The other one here we have in the plot. If we plot with the same scale, here we can see that in the other one, with this scale, plotting with the same scale in both, we have reduced with this diagonal the cracking. Well, and also the behavior. If we perform a pushover analysis in this wall with horizontal load, also adding the vertical pressure of the building, we can perform different pushover analysis in the different levels and improve this reinforcement. Also, we can check different reinforcement configurations to check these other holes and these other walls.
In case we have windows or...
Here we are going to plot the last one.
The thing is always it's easier to model the smaller structures, as already we know the forces and moments and boundary conditions coming from the big multi-story building. The resources taken into account now is always less, as you know, because we have less number of elements. And as we are adding non-linearities as well, it's better to always to work with small models.
Well, here we can plot also crack. And well, here with this option, we can plot cracks, see the crack patterns in my model, and just the design my reinforcement taking into account these crack patterns, adding some more reinforcement where I can need it due to this nonlinear analysis. Well, after analysis these walls, we are going to analyze the next part of the building, that is the beam column joint. For the beam column joint, we can perform different analyses. If we solve with elastic linear behavior, we will have this straight line with elastic linear behavior. We did it, and then we check by code. We check by code, taking into account nonlinear behavior, and we see if we needed more reinforcement or not. Other way to perform nonlinear behavior of this building is modeling this bending moment curvature behavior of beams, here with nonlinear springs on these connections. With those behaviors, if we are solving with first order results, we will have this polyline. On every of these points is when the bending moment goes over the limit of this union, and we will have a pin connection. So performing that type of analysis, we can get this type of pushover result. Instead of solving with that, if we have taken into account second order effects, we will have this other behavior here on bottom, and if we use, as we are doing in our case, distributed plasticity in all the beams, we will have a more conservative results, more realistic results, that is the bottom line. So that is what we've done using solid elements for concrete and trusses for bars, and performing this nonlinear analysis to obtain the ductility and the possible collapse of the structure. If we see the model, here, cycle load. Well, this is the reinforcement. We have different bars, straight bars, and with straight ropes in the two directions, one for the beams that goes inside the column, and well, this is the configuration. In this, I didn't add any special reinforcement for seismic behavior, but well, we could improve it if we need to get a better ductile behavior of this union. Also, the concrete here is modeled with solid elements. Here you can see the mesh doesn't match, the nodes don't match between one part and the other. What we did is 3 different independent volumes, and we use contact elements for gluing them. The contact elements, here we have, it's very easy to create contact elements. Here in meshing, you create contact elements, and then you select one, clicking, and then the other clicking, you have it, click here, and then you define that this contact should be glue. So the behavior is completely glue there. Also here you can see the reinforcement bars. Also the mesh doesn't match with the solid elements. It's not a problem because we have an option here that is insertion. In the insertion, we select the host element, that is this, and then we select the bar that we are inserted in the concrete. Clicking here, then the behavior will be completely together as if they are sharing nodes. So in this way, it's very easy to generate these models, generating volumes, insert reinforcement. It's very fast, also using those loops to create reinforcement bars and these loops with the Python commands, and solve the model. And well, what we've done is also apply symmetry boundary conditions on both sides, and vertical pressure equivalent to the axial force we have in the different parts of the model, and then apply lateral loads, cycling loads. These loads here we have applied different 1, 2, 3, 4. What we are doing is apply some loads. Here we can see. Here we apply first some loads in one direction, then in the other direction, and so on. So we are applying different cycling loads to get this behavior of this union. We could also perform a pushover analysis, just horizontal load until the model doesn't converge. It means collapse of the structure, and get the capacity curve. But with these cycling loads, they are smaller than that pushover analysis. These cycling loads, I will have a progressive damage of the structure, and the behavior will be much closer to the real behavior of this joint under a seismic load that are cyclic loads. So here I'm going to load the first cycle, which has 15 load steps, and I'm going to plot displacement versus force in the bottom node, that is node 57. Okay, and we can see we have a parabolic behavior on this model. Then I apply, I remove the load, we'll have the other behavior, and apply the opposite load. Let's see some results at the end of the first site. Here, well, we have here the deformed shape with these lateral loads. Well, I'm going to remove the loads. And well, here we can see I apply a load in this direction and I had it. Let's see first concrete cracking. Set component of concrete cracking. It will be concrete cracking here on the column. Well, if I plot without average, I can see here I have different cracking lines. I plot average also, and well, I can see I have here mainly cracking. This is the cracking strain, that is this value here in the explanation of the model. That value is well, the strain we get following this line until cracking and this softening behavior. So it's in some point here. Also, other way to see the real crack strain, here the crack width is taking into account the strain on reinforcement. There's a relationship between stress strain on reinforcement and crack width. So we can also analyze the crack widths we are having. Well, also let's see in the other direction, instead of in X direction, the crack width. Here we can see we are having also cracking here and here due to this bending. Well, also we can plot cruising. The way to plot it is equivalent plastic strain. Here we can see we are having compression failure in this part, or shear failure as well, because the equivalent plastic strain is playing shear or compression failure. Well, let's see now the reinforcement. I'm going to hide the solid part, and this is the reinforcement. So let's plot equivalent plastic strain as well. And here I can see I have yielding problems in these bars. Well, after applying those cyclings, loading and loading, loading and loading, here we can see the results if we put them all together. Here we have those results. The model stopped converging after cycle number 5. Here we are plotting forces and displacement. Displacement in millimeters, forces in megapascals applying on the bottom. So we can see the first cycling is more from lighter to dark. Here we can see the first cycle, loading and unloading, loading with progressive damage, loading. And well, the first one is more parabolic, is due to concrete failure. And the last one is more yielding of the reinforcement, because most of the concrete has a big damage. So well, it's more straight and bilinear, and the first one is parabolic. We can see here the last unloading, loading in the other direction, and unloading. It makes this behavior until it breaks down. Well, we could use as pushover analysis result, or for those springs to model the union, we could use the envelope of the maximum values. So if we use the envelope of the maximum values, this is the dark line. That goes is the envelope of maximum values, and it could be used as pushover. If we compare this line with the envelope, here we have the pushover with the envelope, the pushover goes higher. The difference between one and the other is the damage that was generated due to these cycling loads, which is smaller, so it's more conservative. And finally, we can solve a real nonlinear transit analysis with concrete nonlinear behavior and with an accelerogram or a displaceogram in the base of the model. So here in this model we are using concrete blocks with contact elements between the different concrete blocks, and we are applying this accelerogram, and here we can see as this a small displacement slippage between the different concrete blocks. Also we can get cracking, any other result in this big model.
You can apply accelerogram or displacement grams, anything that has different values along the time. Okay, all the non-linearities available in the software can be done even in a static and in dynamic analysis.
Well, the next example we have is a detailed analysis of a Girder bridge, and well, we are analyzing just the Anchorage zone. Here we have some real models, and we try to model what it happened to these real beams. Well, here let's see first the model.
So you're seeing how easy it is to perform always a simulation of real models with this software.
Well, this is the concrete part. Is also modeled with solid elements with non-linear behavior. And well, if I hide it, and well, I'm going to plot all the tendons. Here we can see we have tendons inside the tendon cast. So we have two different elements and the tendon cast. What we've done is that for the cast, we have done also we have used the insertion option. So if we plot all together, we can see the mesh here also doesn't match, but we did with the tubular section insertion inside the concrete, and then between the tendon and the cast we can have an slippage because it's not connected. We can use contact elements between them or coupling equations. We have used coupling equations in this case also for the compression. Here is the Anchorage stamp, and for the area to cover the area of the strap here. So the way to make these connections is also here in the mesh. We can use connections. Here we select one node, and that is the master node and the ties node. After selecting it, we give the behavior. Here in our case, I can select model utils, and here we can see the behavior is rigid because I'm completely connected it. But we can select different options. Have a coefficient and a spring and couple it, well, rigid, different options. We can define an equation just to model a certain slippage or something here for more detailed. And then from this other end, I apply the tendon press stress, a force on the tendon here. So I will have here compression and see the behavior of this, and if I need to improve reinforcement. So first here I'm going to load the result. Here, well, the model was solved in 8 steps. I'm plotting the last one. And in example, I'm going to plot the stresses, results, for misses equivalent stresses, in example, and plot them. And most of the stresses, these high stresses, are in the tendons. So just to see the concrete, I'm going to hide the tendons and plot those results again. Well, I can see here in pounds per square inch the compression loads here in this part. And well, we can take the units and plot them in any other unit for, well, the different sort of units people are used to manage. Here, well, the compression loads. And well, let's see if we can have any cracking problems in my model. So we will also plot here a crack width, component crack strain, and here we can see some crack patterns here near in both sides, crossing them in this part near the tendons.
Connection of tendons at the
So
end.
well, analyzing this with the results, you can find here we have some lines, some pattern lines similar to what it's here, having here, some others following the others. So well, we can analyze in details the behavior of concrete and improve the designs and in our models. And well, the next thing we are going to see is the macropile creep analysis. We can add to this a nonlinear behavior, compression, tension, cracking. We can add also creep analysis. With the creep analysis, we will have a strain during time here due to compression loads, and we are going to analyze it in this member that is a micropile. Here, if I open here the next model, here, well, we have an actual load here, and we've solved it for different times. Time 10, 25 days, 90, well, whatever. Just to activate this, it's when in the material, concrete material, here we activate cracking. Cracking here we can activate it for nonlinear behavior. Well, first nonlinear behavior, then activate isotropic hardening. In example, cracking, we can select cracking with a cracking stress and whatever. So well, and the other way is creep and syncrates here. Creep and syncrates, I'm going to use creep step by step. Also, we could solve with a syncrate analysis. And I'm going to use the Eurocode to analyze it, and I have to set relativity humidity, equivalent thickness, and creep coefficient from these tables. That is the H coefficients that are defined by the AFTID code. So well, applying here the load, I'm going to load the results. These are the results, and I'm going to plot in this. I'm going to plot the graph of creep deformation due to this load, normal load. So X component of creep strain. The axis X, Y, or whatever are the element axis. In my case, X is the longitudinal axis. So I click here, and I can plot it, that value, this is the maximum value, or I can get the graph. I'm going to get in the first element here, that is element 20, node 11, and integration point 1. Press OK. And well, here I can see the creep. The creep strain, negative in the bottom direction, it's compression, and well, this is the curve for the different days. Well, if I plot the stresses, here you can see in my model I have two sections, one inside the other. This is a micropile. I have here steel section and concrete section. If I remove concrete part, here is the steel tube. So I have a mixed section, steel and concrete, and well, When I apply a load, I will have due to creep, well, the stiffness will change in the model, so stresses will be increased on the steel part and there will be a reduction in the concrete part. So let's see stresses also in the model. X component of stresses also in the same element, 20, 11, and 1. Okay. Well, we can see stresses in concrete starts, let's see, in Pascals. Oh, sorry, it's not there. Here, 20, 1. Here we can see megapascals. Stresses starts here in this value, 13.4, and well, it's reducing in concrete due to creep until this value about 11.9. And well, in steel it will happen the opposite behavior. If I get steel result, the element of steel is 10, 11, integration 0.1, press here OK, and we can see stresses is increasing in steel due to this creep behavior. Well, here we have all results together, and well, we can combine this creep increase behavior with any previously nonlinear behavior, and we can perform, in example, a damaging increasing behavior due to creep, how cracking is increasing due to in a bending plus compression girder. The compression is creating and the tension is creating creep, so it's increasing deformation. Also, we can model steel reactions due to tension, so crack will be increased during the time due to this behavior. So we can perform many nonlinearities together, contact, as we see, this insertion. So well, CivilFEM is very powerful for combining all these type of nonlinearities and perform a really detailed analysis. Well, as a summary, just after seeing all the examples, the applications of civil advanced concrete modeling is very, very huge for all the concrete models, any concrete model, beams, cells, reinforced pre-stress, mass concrete, we can perform it. We can design by codes and standards. We have a long list of codes to design for bending plus axial, shear, in-plane shear, cracking. And well, in some zones where those codes cannot be used, like distributed regions, there are those regions where stress distribution is not linear. We can use this nonlinear modeling to get reinforcement. Also, in all these distributed regions, to get reinforcement and design correctly. Also, we can analyze if our models are ductile or not ductile. So that is, we can obtain the capacity curve of the model for lateral loads or vertical loads. That is for performing pushover analysis or failure analysis. We can also get progressive damage instead of pushover cycling loadings where progressive damage taken into account creep cracking to couple analysis, construction stage process. Well, what the construction stage process, we should see them in next webinars. Well, there's a big long list of applications that can be used for CivilFEM, for bridges, buildings, any type of concrete models. And well, with this advanced concrete modeling with CivilFEMs, it allows the engineers to increase the safety of structures more exactly, having more details, what is really happening in the model, where are the weak points of the structure to reinforce it with retrofit analysis. Also, we can perform margin analysis for loads, possible loads higher than the design loads, the loads we took into account to design. What happened if we have higher loads? We will have ductile behavior or suddenly collapse. Well, we can also optimize structures. And well, basically, CivilFEM lowers the barrier to nonlinear finite element analysis for structural and civil engineering by combining a very advanced nonlinear solver with a friendly, easy-to-use graphic interface for a variety of important problems with single or multiple nonlinearities. If you would like to have some more information about the software, you can check the website. The website here, CivilFEM.com. Website in the CivilFEM.com, you can check here the next webinars. We will have much more advanced concrete modeling, but the next one is about the steel. Save the date for Wednesday, 1st of June. And well, you can also, if you are interested on the software, you can also check our partners all over the world. Here we have the location of the partners, the nearest partner we have in your country. You can contact them or contact us for having some special demos or checking the software with a temporary license. Well, thanks for your attention. And well, Ronald.
Yes. Thank you very much. As you have seen, you have a lot of utilities, from simple to advanced utilities to perform real cases. Okay, real cases. That it's very easy to perform it with CivilFEM compared to other software.
And well, now we are going to answer the questions you are typing. We've seen you are typing some questions. We couldn't do it now, but we are answering you by email. Okay, thank you very much for your attention.
Okay, bye.